Modeling with differential equations. We will introduce differential equations and their models. A differential equation is a mathematical equation that relates some function with its derivatives. In applications, the function usually represents the physical quantities and the derivatives represent the rate of change. The equation defined a relationship between the two. These relations are very common. Differential equations are applied in many disciplines, such as engineering, physics, economics, biology. A differential equation model relates a quantity q and its rate of change dq over dt. Given a quantity at a certain initial time t sub 0 and the rate of change, which is the derivative, the goal is to estimate the quantity q at any time t greater than t naught. For example, if there is no immigration and emigration and we assume that all other factors are missing, such as natural disasters, pandemic, disease, the rate at which the population is changing is often proportional to the population at any time. The larger the population, the faster the population is growing. And so if we let P represent the population at any time t, then dP over dt equals Kp. K is what we call the constant of proportionality. This equation implies that the rate of change of the population is proportional to the population. For example, the rate of which the population is increasing is 3% of the current population, then dP over dt equals 0.03p. K is therefore dP over dt divided by p. This is called the relative growth rate, or a percent change per unit time. The expression dP over dt, which is the derivative, the rate of change, is called the absolute growth rate, or the change in the population per unit time. It is the derivative of p with respect to t. dP over dt is called the differential equation, and since this is the first derivative, it is known as the first order differential equation. Note that in this case, dP over dt is not necessarily a function of t. It is not necessarily in terms of t. If k is positive, then the differential equation represents population growth, and if k is negative, then the differential equation represents population decay. The larger the rate, the larger the population increase. The goal is to find the solution p such that dP over dt equals Kp. But if p equals f of t, this is a function in terms of t, then dP over dt equals f prime of t, but dP over dt is Kp. The only candidate for p that satisfies this condition is the exponential model f of t equals p naught e to the kt, because f prime of t is p naught times e to the kt times k. But this is k times p naught e to the kt, and p naught e to the kt is p. And so we have our first differential equation model. Every solution to the equation dP over dt equals Kp can be written in the form p equals p naught times e to the kp. From now on, if we have y prime equals ky, then y equals y naught e to the kt, or y equals y naught e to the kx, depend on what independent variable we're using, t or x. This differential equation is called the first order differential equation because it involves the first derivative.